So, good morning, everyone, and welcome to my talk on software analysis from security perspective and what we are doing and what we would like to do in the near future. So, about me. So, I joined Technology Innovation Institute very recently, and before that, and there I lead a group called Software Security Analysis, and this is a very generic group which focuses on typical software programming, program analysis techniques, and we kept it kind of like a little bit generic on purpose because we would like to poke our nose everywhere, all the project that we want to do, because as I will try to convince that software program analysis remains a basis for most of the typical software security tasks that we see. And before joining TII, I was a professor at the University of Bristol, UK, and there I was also part of a cybersecurity group, and also conducted few workshops at various levels there. And before joining Bristol, I was part of FUSAC, Vrije Universiteit Amsterdam, and in fact, currently as I'm speaking, my ex-colleagues are speaking on your left there about some work. Okay, so I was also there at the same group which they are presenting. And I also spent some time at Verimac, France, which is a very good lab for program verification, where basically I started doing a lot of program analysis from binary code perspective, and so on. So about the talk. So as I joined TII very recently, and our research center is a very new research center, so we don't have actually a finished product to talk about, but we have blueprints. So most of the time in this talk, I would be just talking about what we plan to do here, and basically I will be talking about some of the dimensions that allow us to really build a secure software. Okay, and I call them as a automated star properties, and then star means several things like vulnerability detection, some mitigations, and I will discuss some of those dimensions. And during this talk, I would like to emphasize, or would like to convince you that there has to be a balance in all of these dimensions in order to really have a secure software. Focusing on just one may not yield a very fruitful result. And I would also like to convince, or would like to, let's say, give some ideas about how we should go about it. And as a security community, this is my experience also, that we have to look at the neighboring research community also in order to take ideas. And I have seen, because I have worked in different communities focusing on the very, very fundamental work, theoretical work, verification, system communities, and I felt that sometimes they live in isolation, means the island. That system community works its own way, verification community works in own way, but they are trying to achieve things which may help each other. And sometimes that dialogue is missing, and and the result that we see, that we tend to sometimes repeat research, or sometimes we are not able to do things properly. If we talk to each other, things become pretty good. This has been. So I would like to also emphasize on this part. Okay, so last year I happened to watch a keynote talk by Alex, and I think if you are working in security, then you must be knowing this Alex, because he's also, by the way, author of fifth to seventh edition of Windows Internal. He's a kind of like, a kind of pillars of that generation of hackers who did a lot of fundamental work, and he presented a keynote at Woot Unix, which is a offensive technology based conference, and that was a very strong and very different keynote for me also. And thanks to lockdown, that the talk was online, so I could also attend. Otherwise, it would have been difficult for me to attend that talk. And then what he mentioned there is basically that we are spending too much money and efforts on bug detection. And he made this point that, okay, when he saw some of the thing coming up in bug detection, for example, fuzzing also, and then people also working in bug bounties, earning a lot of money. He said that I have been seeing that for the last several years. At that time also, you were finding a lot of bugs, and today also we are finding a lot of bugs. But thing is that bug finding getting better, but it's not that we are not seeing bugs. You are still keep seeing vulnerabilities. And his point was that, okay, because you have a lot of incentives and you have to do something about it. And then he went on seeing a lot of things, and basically he's trying to say that, okay, we have to change everything. We have to start building software secure since, when we start from the beginning itself. That's the solution. Otherwise, we are never going to end this dirty state of software development. Okay, this resonates very well with what I was trying to do in my research career. So I took some of the takeaway from this. So he said that yes, finding bugs automatically is really important, and it's played a very significant role so far, because that's why we see now many serious vulnerabilities coming up quickly, and people are trying to do something about it. Okay, but then the problem is, as he said also, that if you are just focusing on one side, this is a imbalance, means you just can't handle, because you are getting too many bugs, but you have no way of really fixing them quickly, and that becomes imbalance. So then the point is, here we have a lot of incentives for finding bugs, but we do not have equivalent for fixing bug, for example. Okay, shift left is nowadays this is what people have proposed, that okay, you bring everything related to security testing in your development itself. Yeah, it works, but the problem is that because it is still in the hand of the team who is developing that. It's fine. Okay, the problem is post-release bug fixing is still a man versus machine effort. You have a lot of automated tool for finding, but you can't do anything to fix them. So we need more automation beyond the full pipeline of SDL. Okay, so that's the one takeaway for me from the task. So then what I categorize as vulnerability research means everything that revolves around vulnerability, finding vulnerability, fixing vulnerability, somehow mitigating the effect of vulnerability, and all those things. And so we need to have some sort of balance there in all those aspects here. Okay, so at TII we are trying to do something in this direction. Okay, and so for example, a program comprehension from a security properties standpoint of view, that this is exactly I was mentioning about our group, because we really want to develop skills that allows us to have a fantastic understanding of program, whatever it is. It may be source code, it may be binary code, small, large. We would like to have fundamental techniques inbuilt so that we can really understand first of all what program is, and I will tell you that okay, this is fundamental for whatever task you want to achieve later on. Then in that we have vulnerability discovery, and these are the kind of a blue area where you will see that okay, we are focusing on a lot at CII. And then attack mitigation, this is I will go through one of each of them in my subsequent slides. And then you have attack patching, automated patching, because as I said in the beginning, if you are discovering too many bugs but you are not trying to do anything about them, you are not going anywhere. The software will remain insecure for decades to come unless until we do something fundamental about it. Then automatic exploit generation, this seems kind of odd here because we are talking about building software, secure software, but suddenly why the exploit generation? I will touch something about it. So vulnerability discovery part here, so far we are mainly focusing on memory corruption bugs that are coming from memory unsafe languages, because we know there will be memory unsafe languages. I hope that after some time, when we have more memory safe languages like Rust, Go, this thing will be better. But it will take time, a lot of time, because I don't see that in the coming 5 years or more than between 5-10 years we will replace memory unsafe languages with memory safe languages. It's gonna take time. And then we have actually in this how we do vulnerability discovery automatically. Then we have static and dynamic program analysis techniques that we use. Fuzzing is one of such dynamic analysis technique. But the problem here, because it's a dynamic analysis, it's precise, it's fine, but it's not complete. Okay, and that is why you keep seeing many bugs being discovered now also, because even though you rely on fuzzing, which is effective, but after all, it's a dynamic analysis technique. You are not sure how much coverage, how much complete it is. Okay, then we can use static analysis. Okay, but it's not precise and scalability is problematic. So these are the fundamental problems in both of these techniques. And if you use either of them, you know fundamentally that, okay, there is a gap. You just can't be sure about it. So, and then comes the part analyzing binary poses another problem, whatever it is. Okay, and there we see a lot of opportunity, because we cannot avoid binary code analysis at all. We have to analyze binary code, even though we are working as a coder, writing our own code. And I will tell you a little bit more about it once we start this go in detail. And we have definitely lot of opportunities if we look at this area of program analysis. Okay, and then attack mitigation part, as I talked about. So we know that software will have bugs. That's it, period. We can't do anything about it. And if there are bugs, there will be exploits that will, exploit those vulnerabilities. So there has to be some mechanism that allow us to mitigate those attacks, exploits. You can't avoid them. Okay, then so last decade, I would say, in my experience, was dominated by control flow integrity solutions a lot. People worked on control flow integrity solution a lot, and the effect was very good. And you can see that now even the hardware for Intel, they have come up with their hardware feature that allows you to embed control flow integrity in your software with the help of hardware. Earlier, the problem was it's expensive. If you want to have control flow integrity directly in your software runs slower because of the performance overhead incurred by CFI, control flow integrity. But now you see that the impact is super high. It is like your hardware vendors are thinking about, oh no, we should do something about it. Okay, and then source-based control flow graph flow integrity is definitely better than binary control flow integrity, for obvious reason, because software has more, your source code has more information for you to analyze than the binary code. But again, if you just focus on software, then it's not going to help you much, because at runtime your software depends on many libraries, runtime libraries, whose source code is not available to you, so they are not enabled with CFI. Okay, so then again you're not gonna win the race there. So that is again a lot of opportunity to explore there in that particular part. And then of course binary rewriting is fundamental for all these things, because remember, you are trying to change something in your application. If it is binary, that means you have to have a way of changing your binary effectively. So that's one requirement if you want to go in this direction, and we'll see that what's happening in this. So automatic exploit generation, as I said, that this looks like a kind of odd member of this, all these dimensions, but it is not actually, in my opinion. Normally, exploit generation is a really complex task, because if you want to do automated exploit generation, you have to consider several things, including the environment of a particular victim machine. There you may have a lot of mitigation brought up by your operating system. Okay, you really do not know about that, but you want to do everything automatically. It's a super complex task. Whatever we see currently is not like, I mean, it's really very trivial. So it is very complex, first of all. So if you really want to have a automatic exploit generation which is arbitrary for, I mean, it can take any target and give you a new automatic exploit, it's really not gonna happen, in my opinion, now. Okay, so but then that's good actually, because if we are trying to generate automatic exploits and we know that for many complex scenarios it will not be able to do so, but however if it could, then we know that definitely smart people out there will definitely write an exploit for that. That's for sure, because there are people who are super smart than the current state of automated exploit generation. So if your algorithm could do this, definitely is going to be exploited in the wild. So for you, it's a good measurement of how to fix this bug quickly. So you have a prioritization based on that. So for me, it's more of a prioritization. You still get a lot of bugs, but you really do not know which bug to fix first. This gives you some sort of ranking, and then you can prioritize your efforts accordingly. So for me, it's still a kind of a good member, even though it looks like it's a fancy part why we are talking about, but it's important for me. And then automated exploit generation, I say that it's kind of like a rigorous testing, rigorous software testing. So if you bring in this kind of feature or dimension in your overall secure development, it becomes, I think, more rigorous than just relying on, you know, some static or dynamic analysis. And then auto patching, I said that this is relatively a new area now. Okay, and then initially in 90s, people came up with the idea of autonomic computing. There they were talking about a lot of self properties of the software. Of course, that was ahead of time proposal, but now I think things are pretty good, and we can really go forward in that direction of autonomic computing. So basically what it says that, okay, you once a bug is found or maybe perhaps exploited, also patch can take time still, right? You will file the bug, and then depending on the availability, people will try to patch it. And also, if the bug is in some third party library, it is really out of your hands. You can't do anything about it. You have to just wait for that. Okay, so that's why now I feel that a lot of emphasis is being given to this aspect, and especially if you see there is a DARPA grant challenge also now for the same purpose, and DARPA keeps encouraging people while with coming up with new grant challenges. So this is one of those grant challenges there. So now program comprehension, I come back to now. So whatever we saw earlier, all these dimensions, if you look at them closely, then you will find that all of them involves a better analysis of the system. If you do not have better analysis techniques for your system, you cannot automate that part. And that's the main thing, because you as an individual may look at a particular software, you can analyze it with your own understanding, you can do something about it, but you cannot automate it. In order to do automated way of analysis, you have to go back to program analysis part, program comprehension. So that's why I said it's a fundamental for all these dimensions that we talked about. And then from the security perspective, we also have a kind of whole system, whole program analysis. And to make things worse, you have to sometimes deal with multi-language analysis, because nowadays your programs are so complex. They are not written in one language only. You can, mix languages. You can use C, you can use C++, you can use Rust with calling C function, even other combinations are possible. In such scenarios, you are talking about program analysis in a proper way. It's really hard now. So we really require a lot of new efforts in this direction. And then this is the part I already touched upon, that even though you are the owner of a particular project, you have full access to source code, you may still be using third-party libraries whose source code is not, they are commercial. So you only use them in binary form, but your software depends on those libraries. How you are sure that everything is all right, because there may be problem in those libraries. So you have to have a way of, mixing these two, source-based and binary-based analysis. So this is again a good part, that nowadays actually you also have hardware support that I talked about a little bit, and also some of the machine learning and artificial intelligence. Maybe I think it's a good time to try that. And the reason is not that they are really magic. It's not about this. For me, it's about like complex. The softwares are very large, very complex. Perhaps you may miss many things as a systematic analysis. So bring in a little bit of AI or ML to help you in order to get rid of all those complexities, and let the ML analyze a little bit for you, and then you move forward. Okay. So now we go a little bit of in detail about like what I see, what is happening, and how we can do a little bit more there. So basically, for me, the program analysis means it is like still assisting humans. I think it's not about totally replacing human. It's like it gives some more idea about the properties of the program in more automated way to human, and then let human decide certain aspects. It's very, very difficult to take out human fully, I think, at this stage. Okay. So question to ponder upon for me is like that. What security aspects are important to address, for example? So what kind of security property we are interested in? For example, insecure information flow. This is how your information leak happens. If you are looking for those kind of vulnerabilities, you have to think about, okay, what can I do about it? Okay. Some of the things are, for example, here in the second point, like uninitialized read, null pointer dereferencing, use after free. These are typical memory corruption bugs. Typical, but little bit, harder than the more known form of like stack overflow, this kind of thing. They are a little bit more complex. But the point here is, some of them can be detected by using just a classical program analysis or compiler backend analysis. If you are aware of some of them, for example, even the reaching definition can very easily detect. Oh, it's went back here. Yes, uninitialized read. Just you adopt classical compiler backend technique, and you can do you can analyze some of these vulnerabilities very well. All we need is some sort of creative thinking. All right. So this is what I was talking about, that compiler. And so compiler backend, they are working on very interesting techniques if you are really doing software analysis, but it's still just not software analysis. The same techniques can be adopted to binary code also as well. And then you have verification communities. They are working on verification techniques, but some of those techniques we can adopt for our program analysis, security program analysis. And the venue to look for is like PLDI, Popl. These are the top venues where you have fantastic work coming up. Okay. I will give some examples of that. The scalability, that's I think, main hurdle. The security analysis often require whole program analysis. That's one thing. So if you really want to do something meaningful, you have to have really a full program analysis, and that is not that easy yet, especially given the fact that we saw that environment is very, very heterogeneous. So there are some very interesting things happening. For example, in abstract interpretation, it's a very, very, it's a static analysis, but does a lot of runtime kind of runtime inference of dynamic properties of your program. Okay, so it's a very powerful technique. I will give you some reference in the next slide. Okay. And this is something I put it green because this is very, to me, it's very important area, which is like chain flow analysis. It's like, it's very useful for several security related tasks. Unfortunately, we are still, we do not have very interesting or good solution for it. I mean, there are dynamic chain flow analysis techniques, but they do have lot of overhead. Now there is a possibility of maybe combining some of the recent development in hardware also to come up with a very good chain flow analysis technique. You can combine static analysis kind of thing, and then symbolic and concolic execution. Okay, this is also a very good candidate that we should be exploring more, I guess, and it has got application in almost every dimension that we talked about: vulnerability detection, mitigation part, okay, and automated exploit generation. It's kind of like a fundamental there. I would say fundamental means it's so important that if you do it properly, I think you are good. So there are some recent advancements in this area. For example, SimCC. If you are in this, you might have seen that it changed the whole dialogue there. Okay, because by nature, symbolic execution means symbolically you are trying to understand, interpreting, and SimCC changed that narrative at all. It said that, okay, fine, we can even do something with the compile time, and then it gets you all the information that you want. And then chop symbolic execution, QSIM. Okay, there are many things. And so, for example, so this is the work that I did before joining TII. So I will not talk about this work here, but this is also one attempt towards making symbolic or concolic execution a little bit more usable. Okay, and basically what it does is, like, again, I'm using chain flow analysis to do some optimization to make it better. And this is my main point here, that we do have techniques now. All we have to do, use them creatively, and then they can work in a better way for the given task. So this is source and binary. I touched upon it. So you have to choose whether you want to do source code analysis, source based analysis, or binary based analysis. Fine, but the point here is, if you do binary based and program analysis, it is still fun. I mean, we say that, okay, we have to get our hand dirty. Normally when you are talking about low level binary, playing with assembly code, this is, people typically say that, well, we have to get our hand dirty, but is this still fun? Like, okay, it's nice, like you like it. The problem comes that when we talk about real large complex applications, then it's not always fun. I mean, it's really hard. It is like, okay, I don't see that, okay, that is really fun, I am enjoying it. No, after some time you really get frustrated because it's really tough, especially when you talk about binary code analysis. And in order to make things even worse, multi-language. And now you have C++. If you look at C++ code at binary level, it is like, it's totally mess. And it becomes really difficult to analyze it. So that's what I'm talking about here. It's really super challenging, but lot of opportunities, that's why. Right? So, and binary code analysis is basically a security community thing, I would say, because it's normally security community who is trying to work on it. And this is my point I was trying to make, because it's security community, they are trying to work on it, binary code analysis, but on the same time, it is only security committee, but they are not trying to talk to other communities like verification people or some other people, because they have nice techniques, maybe classical, and you can adopt them, but that communication is not happening much. And if we have that communication, I think this is fantastic. All right, so I will move forward. Exploit mitigation. So understanding hurdles in developing, this is my objective, like why I want to currently, what I want to study here. First of all, to understand that what are the hurdles in developing attack mitigation techniques. So question to ponder upon is, are we discovering new attack surfaces? Okay, because automated exploit mitigation, we need to understand what are the new surfaces that we have to deal with. That means new technologies. For example, nowadays you have like IoTs, right? Lot of IoT devices, definitely they have a lot of new attack surfaces coming up, and now your attack mitigation, you have to consider those things. So that means, of course, if you just consider a typical desktop server kind of application, it takes some input either from the network or your file, and then does, maybe you have to adopt in IoT. Are there newer attack techniques which are fundamentally different? That is also one important part that we have to understand. That's why you can do some mitigation if the attacks are fundamentally different. Your mitigation definitely may not work there, and this is what we see a lot in the previous decade. Like, we came up with new kind of attacks, like for example COOP, which is like counterfeit object oriented programming, okay, and then people come up with print only programming, data oriented attacks, okay. These are fundamentally different attacks, and you really need to have a new way of coming up a new way of defending against them, okay. So we saw already some of the techniques I talked about, that source and binary code, binary label control for integrity. Yes, that's there, and we have a lot of opportunities in binary CFI. Then code diversification, that is another technique, but very not much investigated so far there, because it is also a little bit difficult, because the idea behind code diversification is that each binary that you compile looks different, each binary, okay, and still the functionality is same. So it is not that easy, but if you are able to do it, pretty nice, okay. And then other thing is, which I am hoping a lot on this aspect, like hardware support. That's very important here, because attack mitigation means that you are changing your binary, your program, you are bringing in some new thing in your program which will look for something and react on something, which means there are overhead involved with mitigation. If you are going for only software only solution, this overhead tends to be high. That's why we do not see such mitigations in your typical application. But now hardware people, vendors are giving you interfaces that, okay, you implement your attack mitigation, and we have specialized instructions in order to do some common tasks, and then it becomes super fast because your hardware is supporting you. And I have a lot of hope from that perspective, that with more hardware support we can do fantastic job. I think they are mainly, they may be very specific for a particular task, but we can be very creative, and we can use the same facility to do something else. And then the other part that I think needs lot of improvement is data flow integrity. This is a very strong property, data flow. If you are able to do it, that is something like, okay, it's very difficult to attack your application, very difficult, but it's very expensive also, but because it has to do lot of check at runtime, and those checks, with those checks in place, I don't think you would like to run your application with all those checks. But then again, the same thing, my savior is this hardware, because if we have better hardware support, I think the next big change that we'll see will come from DFI, and I'm pretty sure that in the coming years, it will be DFI that is going to be a hot topic among mitigation. All right, so this is what I was talking about, that so research in programming language community, they are working separately, not necessarily with the security community, but they are coming up pretty nice techniques, okay. For example, these are some of the paper that I saw in programming language community, okay. Complete formal semantics of x86 instruction set. It is really very good, because it allows you now to do a lot of things automatically, because you have formal semantics of each instruction. You can do a lot of analysis. you know that what this instruction does. You can understand its implication, and all automatic. So this is really nice. Similarly, abstract interpretation under speculative execution. Fantastic, because as I said, that abstract interpretation is a technique which allows you to reason about your runtime behavior of your program, but statically. Very powerful. Now what they have done that, okay, we can even reason about speculative execution, which you do not observe actually as a user level program, but it happens internally. And I think what they did is, because of last to last year Meltdown Spectre attack, if you might have heard about them, they were based on speculative execution. The problem in, and now you have a way of, even reasoning your program with speculative execution. And this is coming from, not from security community, PLDI, Popl community. Okay, so that's what my effort was in the beginning, that we need to connect. If you think that we can work in isolation as an island, it's not going to work. Okay, so research in software engineering and verification community definitely doing some work which we can definitely borrow ideas from. All right, so right, automatic exploit generation. Why it is important, how to do it. This is what I think when I start looking at automatic exploit generation. So I already told that my views on automatic exploit generation is not about, okay, we can generate exploit automatically, because this is not what I'm not an offensive researcher as such, security researcher. So that's not my research agenda. So for me, automatic exploit generation is more like a little bit more rigorous testing. But then what's happening in this space? So if you look at that, you had some work initially in 2005, okay, some work. After that, CMU group did some work. You see that, but that is very sparse. 2008, then 2011, 12. After that, you don't see much coming out from there. And then from Sean Heelan from the Oxford University, he did some work in 2009, and after that 2017 he did some interesting work on heap-based exploit generation. Okay, automatic heap overflow exploit generation. And then I saw some 1 or 2 papers recently. So it tells that we are really not progressing very well in automated exploit generation. And that also gives you an idea, also hint, that it is complex. It is very complex. Because as I said, that you have to understand the environment of the victim machine properly in order to really generate automated exploit generation, which is not easy. Okay. And nowadays, and also chain flow analysis that plays major role is not still there. Means it is like it takes time, and it's a very heavy computation. Symbolic execution, concurrent execution, which are fundamental, they are still a little bit heavy for people to apply. Okay. So, and then I am coming to my last part here as far as those main dimensions are concerned. So, automated patching, right? So we saw in the beginning, in fact, this is where all started. Like, okay, you are finding bugs too quickly, but you are not fixing them at the same rate, and that's why things are not moving, smoothly. You do not have, you just keep discovering new attacks, but you do not fix them. So nothing changes, nothing much changes actually. Okay, but so there is a community, separate community, working for decades called program synthesis, automated program synthesis. So the community basically is a branch of software engineering. What they have been trying to do is, given some specifications, can we really generate computer programs? So this is a very challenging task. Of course, nowadays it's becoming reality. Some of them might seen already Copilot, okay, which is integrated in GitHub. It allows you to do lot of program, automated program not rewriting but synthesis, but in a limited way still. But this community has been working for decades. Okay, and then a lighter form of program synthesis is called automated program repair. This is also active community. And so for example, you can see one paper, concolic program repair in PLDI 21. Again, I'm pointing out PLDI, not specifically a security community, but they are working on this also. They were not focusing on as such patching a security bug, but they are focusing on, okay, we can generate some program given something, we can repair some program because there was some mistake or some feature was missing, kind of thing, right? So they are doing totally a kind of complete software engineering perspective. They were developing techniques, but now we can take ideas from them, because after all, patch is again a piece of code that you want to fix and replace with something. Okay, so whole program synthesis is not easy, for sure. That's why you do not see much coming out from there. I mean, you do not, until recently you did not see much coming out from that community. But then the good part is, in my opinion, that security bugs, especially bugs which are related to memory corruption, perhaps they are not very huge patches, huge piece of code, because that is small. Then we do have actually a good friend, because they are the technique is working, may not go on very large code, but then maybe we also do not require a large code. Okay, my just idea, I'm thinking maybe. So this is what so we have been working on some research project. So we were trying to analyze some of the patches, and in most of the time we found that your patches in some of the open sources are not really very big. So this is your original program, and the patch was because you bring in some new condition here, and that condition does something and then carry on here, or it goes somewhere else. So most of the time these memory related corruption, memory corruption related bugs, they have this kind of fix, because out of bound access, they want to stop that. So these are not very big in my opinion. Okay, so and things to solve for patching, but these are the things that we have to really think about. So first of all, we have to have some automated way of knowing the root cause of a particular bug. Okay, if you do not know the root cause of any bug, then you are not going to do anything. But if you are, and also this root cause analysis is also useful for crash triaging. And yesterday night when I was fixing my slide, I just looked for some new research work coming up in this direction. Just 1 week ago in CCS, which is a premier security conference, a team from EPFL presented Igor, and what they are doing, root cause analysis for crash triaging in CCS 1 week ago. So people are really working, and I was super happy about it, that okay, yes, that's exactly the thing that we need to do. And then of course, because this is a patching of binary code, definitely we have to take care of binary code analysis that we talked about earlier. Binary rewriting is the fundamental, because you are changing the binary. Okay, but luckily we have nice candidates nowadays, so it is the right time to do this kind of thing. We can do it, I think. And there is another community which is rejuvenation. So binary rejuvenation is a different community, which what they are trying to do, that given a binary, legacy binary, it was written in late 70s perhaps with some compiler. Now you want to rejuvenate that with the modern features of that particular language at binary level. So this is super hard, but they are working. We can take some ideas perhaps. So I am going to just finish in 5 minutes or so. So now, hybrid approaches of vulnerability discovery. So we have already seen this kind of some separate thing, like I talked about. You have static analysis, you have dynamic analysis, and then you also have hardware assisted features and perhaps some other machine learning kind of thing. But how we can combine them. Okay, So one thing is that what type of vulnerability again I am thinking about. So memory corruption vulnerabilities are there for the last several years, but still you see that okay, new CVE is for a typical vulnerability, memory corruption vulnerability is assigned. So they are not going here, they are still there. Okay, now and even we are not even talking about these logic bugs, forget about, because what we are talking about memory corruption bugs because we can observe them clearly. Logic bugs are even people not talking about. So perhaps what it gives us that maybe we definitely need some sort of combination of several type of analysis to solve this problem, because individually we are, I think, not doing, we are not yet there. Okay, so this is what I was talking about, application of AI and machine learning. So large complex application, so it means that difficult to comprehend. So then we can maybe perhaps take the help of some machine learning or artificial intelligence, but in a more creative way, rather than like okay, just take whatever comes to your mind and just give it to machine learning, it will do some magic and you will get some answer. No, I don't think that that's the approach. We have to have a very meaningful way of combining them. But and you see what's happening. First of all, yes, people did some work to use artificial ML to find binary label function recognition. Those who are working on binary label, you may be knowing that this is not that easy all the time. Okay, sometimes highly optimized code or handwritten code may not have the proper signature for the functions at binary level. If you are not able to find functions, you can't do things actually. Okay, and this is, you see, the Unix sec, they are doing value set analysis with deep learning. This is one of the fundamental thing in program analysis community, and they did nice work with deep learning, and then they did assisted alias analysis. So these are the some of the fundamental problems of program analysis. People have been trying to do that correctly, but given the size and complexity of the software, classical techniques, if you want to apply them as it is not, they are not scalable. Sometimes they give up. But here people are doing a kind of very creative use of machine learning, and this is exactly what I was talking about. There's some creative application, the way you combine these two different communities. It's I think if we are able to do it, we can do very, very interesting work. So I am summing up. So in nutshell, for me, the secure software, as I said, that is definitely you have to have a balance in all these aspects. Okay, and so as I said, a balance across various steps that we talked about. If we are just focusing only on one, we are not going to have that really the secure software that we are talking about. Just focusing on one is not going to help, and we need to look at communities for recent advancement and then try to adopt and adapt solutions from them, and then we can maybe do some better job, I guess. And then, as I said, that I'm really, really looking forward for this, that there is a very interesting development in hardware software interfaces, and this may be a game changer for all these classical but heavy technique to be usable in your large complex environment. All right, so with that I finish my talk. Thank you very much, and if you have any questions you can ask.